Greetings, everybody. Hey, we're going to talk about the sun now. This is in chapter 7, and this is the day star, of course, most important star to us in terms of maintaining habitability for the Earth. And also, we know a lot more about the sun than we do other stars just because it's so close. So this is a great way to learn about other stars. It's responsible for our habitability. It's immensely important. This is the sun in this image right here. And this is a large eruption on the sun, a flare, what's called a flare, which is a huge explosion. Notice the scale relative to the Earth. So everything on the sun, you have to remember the sun is about 100 times the diameter of the Earth. So we're talking big here. Everything on the sun is supersized. Okay, here's the composition of the sun. You can see right away it's mostly hydrogen and a part helium, and everything else that's important to us, all the heavy elements, are sort of less than 1%. That's just the way the sun works. And yet those elements went into making the Earth what it is, and went into making our bodies complex life forms, in other words, possible. So keep in mind that's the composition of the sun. And that's the composition of most stars when they start off their lives. Here's what the sun looks like inside. You're looking at sort of a cutaway version of the sun. Here's the core. It's at about 16 million degrees K or C. At those temperatures, it doesn't matter much. But that means it's very hot here. And that's where it generates its energy. And without this high temperature, the fusion process, which occurs in the center of the sun, wouldn't be able to do it. A few other things that they're showing you here are, this is a word you need to know, photosphere. This is the so-called surface of the sun. Keep in mind the temperatures in the sun are so high that everything's a gas. And so there's no surface per se, but this is the surface we see in the visual portion of the spectrum. It's at about 6,000 degrees C. Above it's the chromosphere. This is a slightly higher layer that we can see also with the right filters in a telescope. It's basically a transition level from the 6,000 degrees of the photosphere up to the 1,000,000 degrees of the corona. The corona is the outer atmosphere. This temperature is still a mystery. It's not exactly obvious why the corona should be so hot. By the way, flares, those huge explosions I was talking about, can have temperatures up to 20 million degrees. That's because they're giving off enormous amounts of energy. They occur on the surface. They're associated with strong magnetic fields. The sunspots, which you can see here, these are areas that are where the energy flow through the surface to space is being interrupted by strong magnetic fields, so they look dark, even though they're only a couple of thousand degrees cooler than the rest of the surface. Prominences of these, that's what you were looking at in the previous image. Prominences can be pretty hot too. Now this is a high resolution image of the surface of the sun. Here we're actually seeing this word granulation. Photosphere, of course, is the layer we're looking at. Granulation simply means this interesting structure right here. You've got brighter elements and between them darker areas. The bright areas are the upwelling portions that are bringing heat from the interior up to space. The dark areas between them are the descending cooler areas that are going back down into the interior. These things change form all the time. Remember, they're very hot, they're gaseous. This changes minute by minute. These things are the size of a middle-sized state. They're not real large. This is a sunspot, a very high-resolution view of a sunspot. Now, the reason it's dark here is because the strong magnetic fields locally in this sunspot are inhibiting the flow of energy. In other words, this kind of energy flow here is inhibited in here, so it can't work very well. These things tend to be a couple thousand degrees cooler than the surrounding area. This area right here is a transition region from the relatively cool area in here to the usual hot surroundings out here. Sunspots come and go. They change hour by hour. Some sunspots are big enough so that they can survive one or more passages around the sun. The sun rotates about once a month. So that's really extraordinary when you consider this is really a hot gas. This is sort of like having an ice cube in a boiling glass of water, but the temperature extremes are even worse than that. Okay. Now, here's this is I told you sunspots come and go. This is actually a plot of sunspot number versus year, starting back in 1600. And yes, remember they did have telescopes shortly thereafter. 1610, people were already observing the sun. First was Galileo. But anyway, this goes all the way up to the current day that you can see past the year 2000. And what's interesting is that about every 11 years, you can see these peaks occur about every 11 years. So we have a peak in the sunspots, and then it dives, and we have a minimum, then it goes back up to a peak, and so forth. Notice the peaks have different heights, so there's obviously some interesting stuff. That's not well understood why that's the way it is. But the big shocker is way back here in 1645 to 1715. There were almost no sunspots, and the sunspot cycle, which peaks every 11 years, disappeared. And no, friends, we do not know why. And this is a big deal because this thing almost happened again shortly after 1800 for the Dalton minimum. And by the way, if you're wondering, were these crazy people that lived in 1645 really able to use their telescopes on the sun very well? And the answer is they were good observers. So we don't doubt their capability to see sunspots. The sunspot cycle was suspended during this time. There were almost no sunspots during this time. It's a big mystery. Today we're going, well, let me show you that. Here we go. This is the sunspot cycle. Today we're looking back at cycle 24. That's the one that just ended. Cycle 23. Each cycle is numbered, and cycle 22. Notice these peaks are descending, and in fact, the peak we just got done with was the lowest in almost 100 years. And by the way, we just went through solar min, a time when there are very few sunspots and very little activity on the sun. That supposedly, theoretically, occurred in April of 2020. And it's hard to tell if it actually did. The best you can do is look back from a little bit of the future as to what actually happened. Now, here's the thing about solar flares. This is a solar flare right here. Now, keep in mind, we're looking at an object that is 100 times the diameter of the Earth. Okay, so look at the size of this thing. And these are the largest explosions in the solar system. And they're not associated with fusion or anything that's going on inside the sun or anything like that. This is due to intense magnetic fields that are getting twisted out of shape and suddenly go a readjustment that forces a huge amount of energy released. This tends to happen towards the maximum time of activity, but they can happen at any time. These things, incidentally, when they do occur, they oftentimes interrupt cell phone communications. They can affect the power grid. There's a real danger the big one could affect the power grid. These things affect international transportation. In other words, commercial jets that fly over the poles to go to Europe, for example, have to cancel their runs because there's a lot of radiation coming into the polar regions because of these solar flares when they come. And all sorts of things like this. The flares, by the way, are like guns. They're directional. If they're not pointing at you, you don't need to worry. If they are pointing at you, you got a problem. Here's the magnetic theory. This is discussed a little bit in the text. You can read it in there. Basically, what's going on here, here we have the magnetic fields I was telling you about on the sun. What happens is that they're like rubber bands. They get twisted out of shape, and it's because the equatorial region of the sun is spinning a little faster than the higher latitudes are in both hemispheres. And you can see that after a few twists like this, you get much more intense magnetic fields because they're being twisted out of shape. This is when the magnetic fields are capable in certain localities of blocking the energy from getting out. That's what sunspots are. And then this whole cycle, the whole sunspot cycle takes about 11 years to work through. There's an 11-year magnetic cycle where the the magnetic poles actually reverse every 22 years. But it's the sunspot cycle that's the most obvious. Now here's the energy source in the sun. This occurs only in the core because it requires 10 million degree temperatures at least to actually make it happen. Well, if you look on the left side, we've got 4 hydrogen nuclei, that's 4 protons. They're going through a series of reactions here. Some are fast, some are not. And what comes out this end is a regular old helium molecule. And along the way, see these gammas that are coming out? This is the energy which we see on the surface of the sun. It comes out as gamma rays, which are the hardest type of radiation there is. And so between the core, where this energy is produced, and the surface, these things go through a lot of collisions, and they are degraded, I say, into visual photons, things we can actually see. If the gamma rays came out unattenuated, the Earth wouldn't be around long, and neither would you and I. So, also there are neutrinos that come out of these things. That's what that symbol means. And neutrinos actually are important because, for example, the photons take about 300,000 years to get from the core to the surface. Now, the light time for a photon is like 2.5 seconds from the core to the surface. Like I said, the reason these things take so long, a few 100,000 years, is because they undergo a lot of collisions. It's like a random walk. They go back and forth and they go nowhere real fast for a long time, and then they finally get out. But these guys, the neutrinos, do not experience any collisions. They're very elusive particles. They literally do a 2.5 second travel time between the core and the surface. And people have been observing these. You can read about it in the text to try to figure out just what exactly is going on in the core with this process. Now here's the interior of the sun, giving you a little different view than we had before. Here's the so-called photosphere that we're looking right here at the so-called surface. Notice that just beneath this photosphere there is this convective layer. That means that the whole layer is being mixed. This is because it's quite warm at the base here. This is like when you boil water in a pan, basically. The bottom of the pan gets hot, the water starts circulating like this. Now, the core is where the energy is generated via this nuclear fusion process we just talked about. We're going to call that hydrogen burning, even though it's not combustion, it's a nuclear burning process. So the hydrogen burning produces these high energy photons, which then bounce around in the so-called radiative zone here for about 300,000 years. It depends on the photon, but that's a good average value. And then finally gets out. And once it gets to the surface, it goes out at the speed of light. And that's what they mean when they say energy transport by radiation. Here we're transporting energy by convection.